What specific problem does the JetFormer method aim to solve in the context of multimodal generative modeling, and why is this problem significant?
The JetFormer method aims to solve the problem of effectively generating and understanding multimodal data, text and images, without relying on pretrained modality-specific encoders and decoders, which can limit performance due to their lossy nature. This is significant because traditional approaches often use separate, frozen models for encoding images into discrete tokens, leading to precision loss and a lack of adaptability to specific tasks. By employing a normalizing flow to create a lossless representation of images and integrating it with a transformer for autoregressive modeling, JetFormer allows for end-to-end training directly from raw data. This approach not only enhances the model's ability to generate high-quality images and text, but also improves its performance in vision language understanding tasks. Ultimately, JetFormer represents a shift towards more flexible and powerful multimodal models that can learn from diverse data without the constraints of prior training on specific modalities.
How does the proposed JetFormer method work? Illustrate the methodology step by step, including the roles of the normalizing flow and the transformer components.
The JetFormer method operates as a generative autoregressive model that integrates a normalizing flow and a transformer to jointly model text and images. First, it employs a normalizing flow to encode images into a sequence of continuous soft tokens, which preserves the total number of input dimensions and allows for lossless representation. This flow model is trained end-to-end alongside the transformer, eliminating the need for any pretrained modality-specific encoders. The transformer component then autoregressively generates these soft tokens, utilizing a Gaussian mixture model, GMM, to model the outputs, thereby optimizing for log likelihood. Additionally, the methodology incorporates enhancements such as a noise curriculum during training to prioritize high-level image structures and techniques to manage redundancy in natural images, ultimately enabling effective multimodal generation and understanding.
Can you provide a simple and illustrative example that explains how the JetFormer algorithm encodes an image using the normalizing flow and then generates an image using the autoregressive model?
The JetFormer algorithm encodes an image by utilizing a normalizing flow model, which losslessly maps the image into a sequence of embeddings referred to as soft tokens. For instance, when an image is inputted, the normalizing flow processes it to produce these soft tokens, maintaining the total number of input dimensions. Subsequently, the autoregressive model takes these soft tokens as input and generates a sequence of outputs modeled by a Gaussian mixture model, GMM. During inference, the autoregressive model generates a sequence of soft tokens, which are then decoded back into an image using the inverse of the normalizing flow. This end-to-end process allows JetFormer to effectively learn from raw images without relying on any pre-trained encoders, ensuring high-quality image generation.
What are the key theoretical and practical benefits of using the JetFormer architecture compared to existing models reliant on pre-trained VQVAEs or other image encoders?
The JetFormer architecture offers significant theoretical and practical advantages over existing models that depend on pre-trained VQVAEs or other image encoders. Theoretically, JetFormer utilizes a normalizing flow model to create a lossless mapping of images into a sequence of soft tokens, allowing for end-to-end training without the precision loss associated with lossy encoders. Practically, this design enables JetFormer to be optimized directly on raw training data, eliminating the need for separate, frozen modality-specific components that may not align with the specific task, thus enhancing performance. Additionally, JetFormer incorporates a noise curriculum during training, which prioritizes high-level image structure and improves image generation quality, a feature not typically present in models using VQVAEs. Finally, JetFormer demonstrates competitive performance in both image generation and vision language understanding tasks, showcasing its flexibility and effectiveness across multimodal applications without the limitations of pre-trained encoders.
How was the effectiveness of the JetFormer method validated experimentally? Discuss the datasets used and the evaluation metrics that demonstrate its performance.
The effectiveness of the JetFormer method is validated through experiments on two primary datasets, ImageNet 1K for class conditional image generation and the WebLI dataset for multimodal generation involving image-text pairs. For ImageNet 1K, the model is trained for 100 to 500 epochs, while for WebLI it processes 1 billion examples per modality, allowing for extensive training on both text-to-image and image-to-text tasks. Evaluation metrics include the FID, Frechet Inception Distance, for assessing image quality, with results reported on ImageNet 1K and MS-COCO for text-to-image generation. Additionally, performance on understanding tasks is measured using accuracy for visual question answering, VQA, and CIDR scores for image captioning. The results indicate that JetFormer is competitive with existing models, achieving high recall and demonstrating the benefits of end-to-end training without reliance on pre-trained encoders.
What specific results were achieved with the JetFormer model in terms of image generation quality and multimodal understanding tasks? Can you summarize the results reported on ImageNet or other metrics?
The JetFormer model demonstrated competitive image generation quality on the ImageNet dataset, achieving a high recall of 0.56, which is attributed to its explicit log likelihood modeling that mitigates mode collapse. In terms of metrics, the model's performance was evaluated using the FID score, where it achieved an FID of 7.84 with an initial noise standard deviation of 64, indicating significant improvements in image quality when employing a noise curriculum during training. For multimodal understanding tasks, JetFormer was trained on image-text pairs and showed promising results in zero-shot image classification and fine-tuning for image captioning and visual question answering, VQA, approaching the performance of smaller pre-trained models like CLIP and Kappa. Additionally, when comparing JetFormer to other models that utilized pre-trained VQVAEs, it outperformed them in text-to-image generation and all image-to-text tasks, highlighting its effectiveness in both generative and understanding capabilities. Overall, JetFormer not only excelled in generating high-quality images, but also demonstrated strong performance in multimodal tasks without relying on pre-trained components.